Hi everyone, welcome to this physical science lesson again. We're exploring electromagnetism, and in particular we're looking at what the magnetic field pattern is around a coil. So have a look exactly what we're doing here. So what is a coil and what's this word solenoid? It's an interesting word. And we just need to make sure that we understand that a coil just means that we've taken wire and we've wrapped it around something. And a solenoid is exactly the same as a coil. It just means that they're used interchangeably. A solenoid is just wire that's been wrapped around an object. That object could be a piece of plastic, a piece of wood, it could even be an iron nail. And that would give you the idea of what a solenoid or coil is. Now, the reason we're looking at this idea of a coil or a solenoid is we started in terms of looking at the magnetic field around a loop. And the first idea that we had was to look at the side-on view, where we recognized using the right-hand rule, the current is going in this direction, so we could draw little crosses going in over here to represent the magnetic field inside there, and we'd recognize on the outside they're little dots, and they're not as evenly spaced, and they're far spread out from each other. And in fact here, this we said was a south pole, because it looked exactly like the field line pattern of a magnet. Now, just to understand what's happening here, we're wanting to do a little bit of a thinking observation. And you might be wondering, what are those round orange circles with a dot and a cross? Well, I want you to imagine what would happen if we took a piece of a very strong saw and we cut that loop in half, and we cut it in that sort of where the red line is. And now we started to use our eye and we looked from the top. Then looking down over here, we'd recognize, hold on, at this point here, from the positive, the current is coming up over here. So we've represented the direction of the current in that position as a loop with a dot in the middle. But over here, the current is moving down. So we've represented, the eye would see the current going down. It's going into the surface. So we're looking down on it, and that's why we'd have it as a cross. So take away the middle bit, and we have our dot and cross. And this is just another view of the magnetic field around this loop, this conducting wire. So how could we represent what's happening? Well, you know what? Let's just use our right-hand rule. And by this time, you should be getting lots of practice. Recognize the thumb points in the direction of the current. So into the board over here it goes, and we loop it around, and we can see that it's got a curve that's going around like that. I've drawn them in, and you've seen this before. These circles that are representing the field lines, notice they're not evenly spaced because this is a non-uniform field. They might actually change a little later on when we have the current moving there, and my diagram might not be as accurate as it should be. These might be pushed a little bit closer together. But if we were to say, so what's happening on this side? We use our right-hand rule, and we say, well, it's going to go down on that side, and it's going to come. It's coming out, so I'll go and stand on this side. It's coming out of the board, and it's going up. So if we now look at my diagram where I've added in those circular field lines, we recognize something very interesting is happening. In the middle here, between these two pieces of wire, the field lines are pointing in the same direction. They're all aligned. They're going in the same direction. They're bunched together, and they're all packed together nicely. Over here, they can spread out. So these ones should really be more uniformly spread. And the overall effect is that there's a very strong upward push or direction of the magnetic field. The magnetic field is very strong between these wires, and we indicated that by the big blue arrow. Now, in which direction does the magnetic field run, or between these wires? Well, let's take a look at the pattern. We'd recognize it's going up over here, and then it's going down over here. It's going up over here, and it's down over here. Does that pattern look like something that you might remember? Let's just draw those lines overall so we can get a sense of it. Something that does that, and going like that, and going like that. Does that ring any bells in terms of this sort of butterfly type shape? Well, of course it does. It looks just like the bar magnet. So we're not surprised that when we said that loop, when we looked at it end on, we saw all the field lines pointing, going into the board, and that they were similar to the South Pole. Well, it's absolutely, because this is where we were looking from. Our eye was looking from this position, which is the South Pole, and this position is the North Pole. Let me illustrate that a little bit clearer so you can see that that point where the field lines, they're coming out of the north on the outside of the bar magnet or of the electromagnet, and they're coming in at the south. On the inside, between the wires, we see that they are running from south to north. On the outside of the wires, we see that they're running from north to south. So just like a bar magnet. And guys, that is a very important idea for us to get together. That it doesn't matter how many ways we look at this. The loop is, hopefully I've convinced you, an example of an electromagnet. And so I've put the two drawings together, and you can see absolutely that they are mimicking each other. They have the same sort of thing. Although they look very different, don't get mixed up now from where you're looking at. This is kind of the top view, and this is the side-on view. They look different, and the notations that we're using are different, but they're describing exactly the same thing. Just to make sure that you've got it, let's have a look and make sure that you are very clear that this is exactly what's happening in our loop. And if we go to our simulation, which we had, or the diagram of our simulation, which I'm just going back to over here, you'll see that's exactly the same thing. We recognize that it goes from south to north, and it's formed this electromagnet. Let's take a quick break, and after this, we're going to see what we can do to increase the number of turns to make this not just a single loop, but multiple loops that will make up a coil. What effect do you think that's going to have? Well, think about it while you have a break.